So in this video, we're going to look at the convergence of improper integrals. In the last video, I showed you what improper integrals were and how to evaluate them. This one's going to focus on just looking at the integral and without actually evaluating it, determining whether or not it converges or diverges. As a reminder, if this integral converges, that means that it will equal some finite value. If it diverges, then we know that it's going to either go to some infinity or the limiting process does not exist. We can't settle down to a single value for this integral. We're going to look at three things. There's always the idea that if I know it has a finite value, I can go to converges without doing any of these three things. But we're going to see the power rules, which are really quick, really easy to do. We're going to see the direct comparison test, which is easy to understand but can be tricky to use. And then we're going to see the limit comparison test, which is a little bit trickier to understand but very easy to use. So let's dive right in. Power rules. There are two power rules we're going to deal with, and they work this way. So in here, let's consider some positive integer c. So 0, or positive number, positive real number c. 0 less than c less than infinity. Okay? Two cases. If I have the integral from c to infinity of 1 over x to the p dx, this means that this will converge if p is greater than 1 and diverge otherwise. The other case we have, if I'm taking the integral from 0 to c, so there are two possible things to make this improper. Either the limit is infinity, or as this type of function, 1 over x to the p, as x approaches 0, this is going to approach, from the right, positive infinity. So these are the two possible cases for improper integrals for these type of power functions. And this is sort of a flip around. So this will converge if p is less than 1 and diverge otherwise. Now notice, for both these cases, when p equals 1, which means that we have the integral from anything, either 0 to some c value or c to some infinite value of 1 over x dx, it diverges, always, for these cases, either having an infinite limit or a limit of 0. Now, on a high level, this should make sense. If I'm going out towards infinity, this bottom will grow quickly because p is bigger than 1, and so the function will go to 0 faster, having a height short enough to make it converge. If I'm approaching 0, then as we get close to 0, this denominator will grow slowly, which then, not grow slowly, go to 0 more slowly, which causes this to grow more slowly and will make it thinner, which will allow me to get the integral to converge. So that's a sort of high-level reason that this will be the case. I like to say, when I have a big limit, p has to be big, bigger than 1. When I have a limit going to 0, p has to be small, less than 1, for these to work. On a higher level, just recall that the antiderivative of 1 over x to the p dx is going to equal the integral of x to the negative p dx, and so long as p does not equal 1, if p equaled 1, we get natural log. So long as p does not equal 1, this is going to equal, we add 1 to this, so x to the negative p plus 1, and divide by that exponent. If p is bigger than 1, this will still be negative, which will cause an x to be in the denominator, and so I'll have something dividing by this infinite value. It'll go towards 0. If p is less than 1, this exponent will be positive and the x will stay in the numerator. And as we approach 0, it will go to 0. So that's sort of the quick explanation for why this rule works. Using it's really easy. So let's look at this example. First one, I'm going to infinity. I want a big power. P is equal to 2, so this converges because p equals 2. Now this one looks a little bit weird. It doesn't look the same. However, you can rewrite this as the integral from 3 to infinity of 1 over x to the 1/2. I'm going to infinity, so I need a large power to have it converge. This is a small power. It diverges because p is equal to 1/2. And the important thing is this is greater than 1, this is less than 1. Or sorry, less than or equal to 1. That would be good enough for divergence here. Now this one, I don't go to infinity, but I also might not immediately realize this is still a power function down here. This is the same thing as the integral from 0 to 5 of 1 over alpha to the 1/4 d alpha. And now you can see, okay, this one, I have a limit of 0, no infinite limit. So I want a small power. The power is 1/4, which is a small value. So in here, this one converges because p is equal to 1/4, and the 1/4 is less than 1, what I needed here. The final one is, just to keep you thinking, I don't go to 0, I don't go to infinity, so this one, it converges. It's not an improper integral at all. I could do the antiderivative of 1 over beta and get the natural log of the absolute value of beta. I don't need the absolute value in this because I'm staying positive, but it's there from 1 to 3. And that's going to be the natural log of 3 minus the natural log of 1. The natural log of 1 is 0, so this is just the natural log of 3. So really quick and easy to use. Once you catch on, find what the limits are, figure out what we need to have happen, and see if it happens. Direct comparison test, easy to sort of understand what's going on. And it says this. So I'm only going to consider f and g functions that are greater than 0 and have, let's say this, are defined in the interval. So I am avoiding these vertical asymptotes. I want to have sort of well-behaved functions, and I'm not going to have the improper integral where I'm dealing with the function going to infinity. Here's what it says. So there are two ways this could happen. The first way, if the integral from some value to infinity of g of x converges, and f of x is less than or equal to g of x everywhere in this interval, then the integral from c to infinity of f of x dx also converges. On the other hand, if the integral from some value to infinity of g of x dx diverges, and f of x is greater than or equal to g of x everywhere in this interval, or actually everywhere from some point on in the interval, then the integral from c to infinity of f of x dx also diverges. And here's the idea, here's the reasoning. If g converges, that means it settles down to a finite value. It has this, in a geometric sense, sort of a finite area. I know f is shorter. All the heights are going to be smaller in this integral. So if this thing had a finite area and this thing has shorter heights, it will also have to have a finite area. This down here, g of x does not have a finite area. The heights were too big throughout this, diverged. If f is even bigger, it has even higher heights, if this integral goes off to infinity, and this one is sort of just bigger, it also has to go off to infinity. So it's pretty easy to understand this, a little bit difficult to use. Here's an example. So when I see this, determine whether this integral converges or diverges and justify our answer, you should jump into saying right away, this looks like it should converge because I have this x cubed. And then you might think, okay, well, let's consider the function g of x equals 3 over x cubed, because that's sort of the end behavior model of this. We know this converges because p is bigger than 1, and I have an integral going off to infinity, but this here is not always bigger than this function. So the problem is, we know that this integral of this g of x from 1 to infinity converges. But unfortunately, this is not always smaller than that. So consider, let's say x equals 9. That'll work out. 3 over 9 cubed, which is 3 over 27, so g of 9 will equal 1/9. Whereas f of 9 is going to be 3 over 27 minus 3 plus 2, which is going to be 3 over 26, which is actually slightly bigger. So the problem is the obvious function doesn't work because of this problem. It's not hard to fix, but this is what makes it a little tricky. So if I, for instance, let g of x equal 6 over x cubed, this still converges because of the power rule. So the integral from 1 to infinity of this g of x dx converges. And since this is bigger, so the 6 over x cubed fixes these small problems here, we know that g of x is greater than or equal to f of x, everywhere f of x is smaller. This all means that this integral from 1 to infinity of 3 over x cubed minus root x plus 2 dx also converges. So easy to understand, but it can be very difficult to find the correct function to bound some of these. Finally, the limit comparison test. And this one a little bit hard to understand, but really easy to apply. So same types of rules before. I'm going to consider two functions f and g. These functions I'll say will be well behaved in the integral. I don't want any vertical asymptotes to worry about. And here's what it says. So as long as the limit as x approaches infinity of f of x over g of x is equal to some finite positive number, so 0 less than L less than infinity, meaning they grow at the same rate, we talk about growth rates, then if the integral from, I'll say, some positive value to infinity of g of x dx diverges, then the integral from c to infinity of f of x dx also diverges. And if integral from c to infinity of g of x dx converges, then this integral from c to infinity of f of x dx also converges. And the idea is this: as long as I can find a function, so I'll write this down, I want to find a function, function I know about that grows at the same rate, then I know that I can tie them together and figure out what happens to the function I might not know about. And it's much easier because the function that I'm looking for will be much more obvious. And the idea is, if g of x does not approach 0 fast enough, causing the integral to diverge, then f of x can't because they grow at the same rate. If g of x does approach 0 fast enough, then f of x also has to approach 0 fast enough. And here's an example. So I look at this and right off the bat I say, okay, this looks like it should diverge because of this p equals 1 here. And it does diverge. Here's the idea. G of x, I'm just going to make equal, sorry, not g of x, g of y, I'm just going to make equal 1 over y. And I know that the integral from 4 to infinity of 1 over y dy diverges. Okay, because this is p equals 1. So all I have left to do is see that this limit, as y approaches infinity, of 1 over y plus root y minus cube root of y over 1 over y has a nice limit. And in here, if I go through and do this, I can rewrite this as y over all that stuff. So the limit as y approaches infinity of, dividing by a fraction is the same as multiplying by its reciprocal, y over y plus root y plus, minus cubed root of y. I see that the numerator goes to infinity, the denominator goes to infinity. Use L'Hopital's rule. I'll get that this will equal the limit as y approaches infinity of 1 over 1 plus the derivative of root y is 1 divided by 2 root y. The derivative of the cubed root of y is 1 over 3 y to the 2/3. And here, the numerator is, of course, 1. It's approaching 1 then. This part right here, as y goes to infinity, goes to 0. This part right here, as the denominator, this y approaches infinity, goes to 0. So the denominator goes to 1, the limit's equal to 1. They grow at the same rate, so this diverges. Feel free to comment below with any questions. I hope this helped you out.